Welcome everyone to lecture 9 in machine learning techniques and structural mechanics. I will be taking care of the lecture today, not Slava. So let's see how this goes. Okay, let's start with a short recap of last week, like always. We learned about RNNs, that they're quite nice for processing of sequential data. And we saw that we can use this gated recursive, gated recurrent units and the long short-term memory units that they enabled us to memorize or forget previous inputs. So improving our sequence processing capabilities even further. And then we have seen that for some more demanding applications, we need to use bidirectional forms of these networks. And that despite this, there are still some disadvantage arising from the sequential nature of the architecture, because we can only keep information as we go along the sequence and can't skip very well back in time there. But we also saw that we can circumvent this somehow with this transformer architectures, which the amazing things we see right now, like ChatGPT, are based on. Okay, today we will do something else. We will focus on generative modeling. So far, we basically had some kind of input and wanted to predict a class or do some regression on there. Today, we want to get some data and we want to generate, for example, images or structures or whatever that are similar to those we have in our data set. So on the left, you can see some of those generated numbers for the MNIST data set. You should all be familiar with. And on the right, we can see something more related to structural mechanics. These are AI-generated floor plans. And these are for very high buildings. And the red walls are actually so-called, I think, shear walls that need to go from the bottom of the building to the top. And the AI is basically able to place them manually. And then, of course, some engineer can look over that and then decide if the design still needs some more tweaking. But this is able to speed up some engineering processes. So what else can we use it for in structural mechanics? I did Slava's favorite thing and asked ChatGPT. And you can see that some of these answers are actually better and some of these are not as good. Not really. So it says design optimization. So basically says we can generate a lot of alternatives and then evaluate these and then pick these that basically are optimal for our application. And that's a very, very cool thing. Quite difficult. Another thing is material component selection, quite similar, that with generating designs with different materials, and again, select based on some metrics our nice designs. And then there are these that are more, it says failure prediction analysis and structural health monitoring. These are not really connected to our generative design. These are more like the feed-forward networks we always know. So yeah, you can see here that ChatGPT kind of mixed some answers for more general AI questions and generative design in there. And then it says simulation analysis augmentation. Which is again more not entirely in the generative realm. It's more like we train a model based on simulations and then use this model to do something else. But it's not in the direction we want to go here. So be careful with ChatGPT. Okay. So we want to generate stuff. how to do that. So what requirements do we have? If we want to do focus first on MNIST, our restriction is, so far, we want to output images. We have absolutely no restrictions or ideas on an input, and there might be some other stuff. So do you maybe have some ideas on architectures or something you might have seen that we can use to create, or at least have in the end, an output that actually is an image? Have you seen some architectures that just output an image so far? Autoencoder. Yes, that's absolutely right. So put in an image and we want to get the same image out. And in between we have this bottleneck. And the big question is, okay, now we get an image here as an output, but how can we use it to generate new images? So something that wasn't here in our training data set. So we want to get something out here that that's not in our training data. What could we do? Of course, one thing is we can put in something here, something whatever, something that's not in our training data. And then we will have something generated here that might not, that's definitely different from what we've observed during training. Or we can just select here in our bottleneck, which is much smaller space. We can basically take this part, use it as generator, and input some variables here. And we will get something out there. The thing is, if we do that, we generate some new images in the end. But we know that when we work outside of our training data, what we've observed during training, we can't guarantee what we get. So if we do this for MNIST, if we don't put a number in, we don't know if we get a number out. So if you just choose a random input, we might get maybe a strawberry, maybe a cat, maybe just some noise. So we can't really control it if we pick outside our training space. So what we need to do here is we need to know how our training data is distributed here. And then we need to sample from this distribution. So that's basically what we've observed. So basically here we have an unknown distribution. And since this, oh, there's a typo. So since this is basically unknown and it might be absolutely complex, we want to restrict this distribution. We want to make sure that it's very nicely with usually a very simple normal distribution. And if basically our training data in this space gets into such a distribution, we can just sample from this distribution and we will get a number out there. Does it make sense what I just said? A little bit? Or was it too fast? An example. Just one unit. Okay, so basically, if we have just one unit here, and our training data, all of our training data is between 0 and 1. This unit always has a value between 0 and 1. And basically continues between them. Then, of course, if we for this unit, if we pick a value of 2, that's outside of our training data, and we don't know what we get here. But if we pick a value between 0 and 1, just some arbitrary value there, and we know that for everything between 0 and 1, we will get, and basically our training data is nicely distributed between 0 and 1. We can just pick a value there. Just pick, for example, 0.2. And then we will generate, based on the 0.2, we can generate an image. And we will know that this is, again, for NNIST, it's a number. It basically constricts to our training data. Good. So for training here, then, this alters our loss function. So we still have our reconstruction loss from our standard autoencoder, but we then get some term here that wants us to fit this distribution nicely here on this bottleneck. We basically want this to be in a certain range and shape. And this leads to something called a variational autoencoder, which is a little bit more complex. And the main difference there is that we are not using these numeric variables we have there. We're using something so-called stochastic variables. That means what we are doing here is that the encoder, it doesn't produce a fixed value, but it produces a mean and a standard deviation. So basically a distribution. And then what we do, the encoder produces this small distribution. We sample from this distribution, and that gets our encoded value. And then we decode this value. So the thing is that now our 9 doesn't map necessarily to the same 9 or to the same encoding here. But since this is basically a distribution, we can, for the same input, get a little bit different encodings. A little bit tiny different. So this way, it basically learns that not only this fixed numbers, this fixed encoding, basically we might have some, if we have just 2 variables, we might have 0 and 1. And if we decode 0 and 1, we will get a number here. But the thing is, when we train a standard autoencoder, if we put in something like 0.1 and 0.9, we can't be sure that this is inside of our training range anymore. So we might not get a number here, because that might correspond to these data outside of our training range. So what we do, if we have a distribution here, we might take this and we don't encode this as 0 and 1, but something similar. So we might encode this as this 0, might encode this as 0.1 and 0.9, or we might encode this as minus 0.1 and maybe 1.1. So something around that. So we make sure that for each training value, for each encoding we get for actually something in our training data, all the encodings around that give us, again, some valid data, something that looks like our training data set. So, and this actually makes this training a lot more stable, that we can just learn the restricted distribution and then just pick some values that are not correspond to encodings of our training data, but they will still give us something that looks like it. Okay, good. I think. So the problem here is that with these stochastic variables, we can get a problem with backpropagation. Because how to train some and get the gradient of a probability distribution. So what we can do here, let's see that later. First, I said we had this reconstruction loss. That's still here the same. And then we have this regularization term, which is just sum. And in this case, we didn't want to go too much into the probability distributions since you don't have a background on that, just to note that this is actually a distance function between two probability distributions here. There are multiple ones, and there's some that are more often used, but just keep in mind there's some, you try to minimize the distance between two probability distributions, so in the end, they are the same. Okay. Now back, oops. Okay, there's actually a slide missing. Okay, now back to what I said. We have a problem here with this sampling, with backpropagation with the probability distribution there. And what we can do a little trick. We can get another function epsilon here. So we have kind of our, this is our mean. Sorry for the different notation. I think this is our variance. And then we can sample from this distribution and get our t. Then, like I said, we can't do backpropagation for that. But if we basically get our mean and our variance here, and get this little tiny epsilon, and sample this epsilon just from a normal distribution with 0 mean and variance 1, we can multiply epsilon with our variance and add the mean. This way we still get the same probability distribution as before, just a normal distribution. But these two are not stochastic, and that not. That also not. We have this, the only stochastic node is epsilon. So we can just do a backpropagation on the side, forget about this epsilon thing, it's not going to change. And with that, we can nicely train these variational autoencoders. Okay, that might be a bit much, but okay. Yeah, so that's for the training details. And with that, we actually get very nice encodings. And the nice thing is that these variables in the bottleneck, which we can also call the latent space, they're actually quite independent in what features they control. So they learn things that actually mean something, and they learn things that basically we can change one variable, and this doesn't mean that we need to change the others. So for one example here is basically the direction in which the face looks. So this is just one arbitrary length variable, and it kind of correlates to something meaningful. Or you can see that I think this is a little bit smiling. It's the other direction. And you can basically change, of course, if a person is smiling or not. You can change that independently of the direction the person is looking from. So you get things that don't influence each other. It's a little bit more difficult for the numbers. But you can kind of see here that, okay, you have here shapes that are more aligned, like a 7 and a 1 on the one axis, or on the Z axis here in the bottom. And here you have very round things like 0s and 6s. And then they get basically from just one curl here with the 6 to a 2 or 8 with 2 curls on the other side. So these are a little bit related, but these are again features that you can see they have some meaning in them, and you can control them. And this is a very nice thing for a variational autoencoder, that they are able to learn such things that humans are kind of able to interpret and use to change the data in some meaningful way. So that's it for the. Oh, I'm super fast. That's it for the version autoencoders. So nice thing is we can basically take an autoencoder, we can modify it such that the decoder acts as a generator. And we can then just sample in this bottleneck/latent space to generate new images. We then have to do a little trick, basically a parameterization trick to get the backpropagation. And from that, we actually get these nice, meaningful, independent features. And yeah, especially the last two with the latent space, these are big pros for variational autoencoders. But there are some drawbacks in the sample quality. So these are often seem a little bit blurry, and compared to other approaches, they are now of lesser quality. So one question, is this approach supervised or unsupervised? Supervised? Yes, it's counted as unsupervised. I'm always not too sure about that because you kind of have your data set. And selecting your data set is a little bit as labeling, these are the things that I want. And then you don't need kind of a second class. So, but yeah, it counts as unsupervised. Thing is, can we maybe learn something similar just without caring for those explicit probability densities and this parameterization stuff by just using some neural network layers? And if we just look at the generator from before, can basically say that, okay, we have some random distribution. If we restricted the latent space successfully in the variation autoencoder, we can call that just noise. And can we put that into a generator and then get some output that actually is one of our admissible images? And in general, we have a problem there because we kind of don't know what noise to map to which image. So we need to learn a mapping like that. Basically, learn to which selection of noise, which image from our nice space, which image correlates to our noise. And we can do that in a very, very awesome way, I think, because we are going to do this in a so-called two-player game. So one player is our generator, and the other one is a so-called discriminator. So our generator has basically the task to do the generation, basically get us something that looks like our data set. And our discriminator gets these, but he also gets our real data set, basically our training data. And for each of these, he tries to decide if they were generated, okay, a fake image, or if they are real. And we train him to do that. And the task the generator gets then is, in order to generate good images, is basically to fool the discriminator. To generate images the discriminator thinks are real. And then you basically throw them in spider jar and train them against each other. So see which one is able to overpower the other. And usually, if this training is stable, the generator learns to generate images that match our original ones very, very well. Yeah, and just do it in math. With math. So this is our loss function, and it has basically two parts. One part is that says, okay, we're trying to basically our discriminator output should get to either 0 or 1. Maximize, I think, minimize, I think it's 0. And so our discriminator tries to output 0 for our discriminator loss. Our discriminator tries to assign 1 to our real images. The second part is it tries to assign 0 for our generated ones. And our generator, he just tries to do the opposite here. Just like I said, they're trained against each other. So let's have the most common example here, how this training works. And it's often compared to counterfeiting money. So we have our generator that tries to design 10 euro bills. And remember that each bill is usually a little bit different. There are different serial numbers on. They may be a little bit wrinkled or whatever. But that doesn't really matter that much right now. So before training, we basically have our training data, which consists of images of real banknotes. And then we have our untrained generator. And since it's untrained, it just produces something, mostly noise. It's not trained to do anything at all. And also our discriminator is not trained at all. So it just randomly assigns values between 0 and 1 to any of those samples. So first thing we train is the discriminator. And we want it, in this case, to assign 0 if it thinks the sample is real. And 1 if the sample is fake. And of course, this works very well because these are obviously fake. So we can separate it nice. Next thing is we're training the generator. What do you think will happen? Just train the generator, keep the discriminator the same. Less noise, yes. What will happen with the generated images in terms of the discriminator here? Where will the red dots go? Yes. And depending on loss, they will get very close. And our fake data will start to resemble the 10 euro bill a little bit more. So maybe get pink and has the tens on them. Next thing is we train the discriminator again. What happens? What happens to this if we train the discriminator? Nothing, because this only depends on the generator. What happens to these dots here if we train the discriminator again? Okay, red ones are clearly false, but if you see here, there's a red one tried to mix in with the blue ones. So the discriminator will think there's something fake close to my real data, and that will mess up its confidence. So it will get a little bit less confident in its real data. But it's still able to separate that. If we train the generator again, the same thing as before will happen. Move these red dots closer to the blue ones, And our fake data will start to look a little bit more like our training data. Maybe you can see the colors of numbers may change and a little bit of details may add it, but yeah, a little bit closer. Train the discriminator again. What happens? Same thing as before. These get split again, but again, our discriminator loses confidence. And if we continue the cycle over a few hundred, maybe 1,000 times, we will get fake data that looks exactly like our real one. I'm so fast. Okay, and our data here will be just centered around a half. Our discriminator can't decide anymore, so he just puts everything in the middle, everything. And if that happens, that's, in theory, our images should converge to this equilibrium or discriminator and generator. But in reality, unfortunately, training these GANs is very, very unstable. And a lot of different architectures, they don't converge. So this is a study from some guys at the Max Planck Institute in Tübingen for intelligent systems. And they basically looked up which very popular GAN architectures converged. So they basically find a configuration in which discriminator and generator are stable. And this is only the case for a very few, including these two so-called Wasserstein GANs. These are some of the most popular architectures. They work, in general, very, very well, but it can be quite difficult to train them due to this stuff. Okay, but there are also a lot of tricks to get them to train nicely. So that's, if someone is aware, that's not that big of a problem. Okay, and from this you can kind of see there are a ton of different, also named, these all have very kind of interesting names, of GAN architectures out there. And someone tried to take track of them, but I think they, in 2017, but after that they stopped, because you can see that these are the papers with distinct GAN architectures that were published each month. In 2017, this reached 300 a month, different architectures. So that's more papers than I can read. And yeah, there are a lot of them. And let's have a look at some of the highlights there. So one cool thing is the so-called cycle GAN. This is very special. You might remember transfer learning. And it doesn't use some arbitrary distribution, but it actually has two sets of images from two different domains, like horses and zebras, or Monet paintings and photos, or summer and winter images. It has just two data sets. It also has two discriminators. And it kind of has two generators. And what each generator does, gets one image as kind of noise, and then transforms it into another image in the target domain. There's another trick not shown here. You, of course, have the two discriminators, but you also say, please make these images not just a zebra image or a horse image. Make it kind of look the same as our previous image. And from that, you can see here nicely transfer the styles. And what I really like about the zebra and horses thing is that, for example, in this picture here, you can not only see that basically the pattern of the horse changes, can also see that the color of the grass changes. Because zebras are mostly in savannas or something where the grass is less green. And that's encoded in the training data of your zebra images. So it also changes the grass color a little bit. Yeah, so this is quite cool. You can learn multiple styles, Monet, Van Gogh, and some others. You can transform a simple photograph too. And you might know that we have a very good computer vision group here in Freiburg. They did something even more fun. They learned something similar for videos. And they basically applied, in this case, the Van Gogh style to the movie Ice Age. And what they did is, if you just do it per frame, all of these images are kind of transferred into the new style, but they don't fit into a row, so you don't get a real movie. And then you can add some temporal constraints, and you can get a nice sequence. And this looks absolutely amazing. Oops. Let's have it here. Yeah. So, oops. This is without the temporal constraint. You can see it flickers a lot. And can see that some things actually stay focused on the background. You might know this place. And then you can transfer it, and you can see that the people are moving nicely, but everything in the background stays the same. You can apply this to a lot of other stuff. Just this is especially nice shot, I think. So you can see that things keep their position very nicely, style transferred in the background. Yes, YouTube. Yes. What the? There. Okay, and the third one is Pix4Pixscan, and this can do something also quite cool. It can, from very simple conceptual images, it can generate real images. In this side facades, can just take some colored blocks here, and it will draw correlating features here in the architecture. You can see this was the ground truth image for this particular pattern, and this is what gets actually designed by the neural network. A little bit different style of the building, but you can see that basically the window arrangement is fit very, very nicely. Okay. So what we've done so far is we looked at these unsupervised techniques for both the GAN and the autoencoders. But what if we want to basically say, okay, I want to train a general model that generates MNIST images, but if I generate something, I want to be able to decide which number it shows. So basically be able to say, I want a 9, or I want a 6, or whatever. So let's have a look at our standard GAN architecture. Do you have any ideas how to inform them what to generate? Basically, we have our data set, MNIST, and we somehow want to tell this, I want a 9. How can you do that? Ideas? Yes? Then it can only generate 6s in the end. We want to basically be able to generate all the numbers, but we want to tell it, right now I want a 1, or right now I want a 2, 3, whatever. And of course, we need to tell the network somehow what we want. So we need to inform the generator. And then we need somehow to conditionalize the generator to do what we want. So can add an additional input there. And what we can also do is then we don't generate we generate the image, and then we take our class here and pass the class image pair to the discriminator. Same thing for the real data. We have class labels here. We need class labels there, and we pass the class and the image to the generator. And then we just do the same thing. We treat this pairs exactly like we treated the images before. And with that, we can kind of learn that, okay, I have here an image that shows a 7, but I wanted a class 8. So a 7-8 combination, that's obviously fake. It should be a 7-7 combination. And with that, the generator actually learns, okay, I put a 7 in here. So I have a 7 as class. So I need to generate a 7. Otherwise, I won't be able to pass the discriminator. So you get the proper pairs there. There's a little problem with this architecture. And that problem is that these combinations are very, very difficult to learn. And they're very difficult to infer from the data. So your network might just say, okay, or the discriminator might just say, okay, I got an image that looked like a number, which some class. But in the early stages, the discriminator will just focus on, did I get an image that looks like a number, or did I get something entirely else? So it might just disregard the classes because they're not that important. It will just say number and image or not. And with this, it might just learn to ignore the classes completely. So we need to find a way to force the discriminator to pay attention to the classes. You have any idea how to do that? Okay, that's quite a difficult question. But what we can do is, instead of passing labels there, we can say, okay, our discriminator outputs a class. And we force this class to be the same. Here we again have the data. Basically, fit our real images. And what we also do is to say is, okay, if we put in here a certain class, it should also match here. And with that, we can force the discriminator to pay attention to the class because it has to predict the classes of the things. Okay. And yeah. Good. So for summary, we saw that we can train this network adversarial in an adversarial way by training the generator and discriminator. Can also learn a nice mapping between noise and the images. And we have seen that there are very cool GAN architectures for different tasks, for video generation, of course, image style transfer, and yeah, of course, there are basic ones for MNIST and other standard problems. And okay, again here, the learned features are independent. And these GANs usually give very good samples, and we can use them for a range of applications. It's transfer learning, so it's very good. But the cons is that training is very, very unstable. And there are a lot of arcane tricks, so a lot of papers out there that are concerned with how to make GANs train properly and nicely. And that can be sometimes a real pain. Yeah, and the thing is, compared to the autoencoders, for some applications, it's really nice if we learn those probability distributions. They are sometimes difficult to learn or restrict us, but for other applications, it can be very nice to have them. So what have you learned today? And I terribly underestimated the time. I'm sorry, Slava. Good. So we saw both variational autoencoders and GANs, two generative architectures. We've seen that the variational autoencoders it can expand on the standard autoencoders to get the generation with the scene reparameterization trick. And yeah, again, we learned about the GANs and some cool GAN architectures. And we also learned that we can very easily conditionalize the GANs to different approaches. And that's quite nice for a lot of examples for especially if we think back to the ChatGPT thing in the beginning, if we want specific properties. So basically, if we have a structure and we want the structure to have maybe a specific stiffness, we can also conditionalize on that. So we can learn to generate structures that have exactly the stiffness we want. Okay, and that's it. And yes, I think Slava has something.
No, I think that's actually very good introduction to generating things. We will talk about the next lecture as well. We will mention very modern diffusion types of neural networks, but in order to go there, you need to understand the variation of autoencoders and GANs. I think these two approaches are still quite valid approaches, and you can use them. If you train GANs, be careful. It's really hard to train. This is actually one of the topics of Gerrit PhD thesis, when he's working on GANs on a quite nasty input space, and GANs are very bad for that. However, if you're using images or videos, it's a way to go, especially if you can use pre-trained models. And for variational encoders are probably even more stable, in terms of training. They are not so powerful, but at the same time they're really stable. So there are other methods, and in particular it's diffusions. And during the practice on this Thursday, and during the next lecture, we will cover some of these topics a little bit more. And in practice, you will try to play with the generations of the. We'll see what exactly you will generate, but I hope that practice will be as fun as last time with the YOLO algorithms when you detect objects. So we will do a generation. So, but now, since we usually have this very cool thing to show and share some papers,
you already, when you did the home project number 1, you already saw some generation if you read the paper that we published. So you did only the prediction classification problem, but we have, of course, a big part of this paper, and that's exactly why it was published. Its approach to generation. So in our case, let me just see if I have this particular paper on the class 1. I think I can download it from Ilias, and that's what I will do right now. Ilias. Let me just move it here first. And login. Well done, login. Like machine learning approaches and structural mechanics, home projects, home project 1. We download it, and now I will be able to open the manuscript itself. Let me move it here. So this is a paper that we published with Gerrit. And again, what you probably did before during the home project 1, we just discussed this, which one? Generation, the right part. So you have some geometry and you get Poisson ratio. So, but of course, much more fun we have if we want to generate the geometry for the desired Poisson ratio. It's called so-called inverse problem, and it's a very common problem in any types of engineering. When you don't care about prediction of properties, you care about the generation of materials or structures with the properties that you want. So in this particular case, what we've done, let me scroll it a little bit down. So I will just want to, we will skip the theory. Again, you should be already familiar with the forward problem. And what I would like to show, a machine learning implementation for inverse property structure problem. So, and here we didn't use any of the of these architectures that Gerrit showed. You can somehow argue that it's close to encoder. And it's actually, it's encoder. It would be correct to say. But since we were lucky to have a very nice design space, we didn't do the tricks with matching of the probability distributions. But in general, what we've done, let me just show you. Again, this is the same picture again. Maybe, and you actually see that we had, this is our loss function. And our loss function consists of 3 components. First component, it's actually matching between the properties, right? So it's exactly this sort of what we call reconstruction problem. So we see what we want as a Poisson ratio, and we see what we've got during the training. So, and we compare them, but again, just mean square error. The second part is much more interesting. You see, what's unusual in this architecture that we provide here is this middle point, when we have something that is called prioritize. Why did we do that? And the answer is really, really simple. Because, and I think Gerrit already mentioned it somehow, if we have architecture that looks like you see, unusual part here, if you look at encoder-decoder configuration, it usually looks like that, right? So you have a lot of data, you have a lot of variables, you shrink it to the bottleneck, and then you expand it back. Agree? You saw that previously. Unfortunately, when we did it, the problem that as input variable, we would like to have Poisson ratio only. So we actually have a very strange architecture that looks mostly like that. So we have a Poisson ratio that we want, it's called target Poisson ratio, and we have a Poisson ratio that we generate. And if we just train this neural network directly, what we will have, and somewhere here basically the structure is generated. For each Poisson ratio, we will have only one solution. So if we want Poisson ratio 0.5, or like, let's say 0, we will get solution. But we have no ability to randomize it. So that's what you saw in these images, in the videos, and in the GANs, in variational encoders. It's cool that you can randomize your output. For the same label, for the same, let's say, image, like, or for the same image of 6, you can generate multiple different 6s, right? In this approach, when we train it directly, we get only one output for Poisson ratio, and it was quite boring. So the idea was, and that's something along the line of the variational encoders and GANs, to add additional parameter. And in this case, what we add, we say, okay, we just don't want only to get the specific Poisson ratio, we want our curve, our unit cell, to look similar to another one. So we add what we call this case guide curve. So we not only want to Poisson ratio match, but we also would like to have some preferences in the shape selection. And that actually, again, this is this term, right? This is this term. Yeah, this is this term. So we start to look not only on the Poisson ratio matching, but also how far our new generated structure is from our desired structure. And that's, again, there is some balance coefficient, because we cannot, let's say, do it sometimes simultaneously. We need to kind of have some trade-off. And finally, there is another so-called penalty factor to disallow our curves to look something like that. We, of course, when we generate something for mechanical engineering, we would like to have our structure. That's very nice. It's very nice. Yeah, this is still. So if you imagine unit cell, this is our original unit cell. We can allow something that looks like that. It looks reasonable. But what we don't want to have something like that. So we in this particular term, we just really penalize the deviation from the straight line. So if our deviation is beyond some specific range, we say, okay, that will be some factor penalty, and since we want to minimize, all our solutions should be inside. So this is quite easy to implement trick. And what I want to show at the end, what we get. And I think we have, again, we compare our properties. Properties is quite easy to compare. Again, you just look at the target Poisson ratio that you feed into your system and your generated Poisson ratio that you get output of your system, and then you say, okay, they are almost identical and we are fine. But what's more interesting is what happens with this one, with the resulting curves. And here is a very good example. I think on the give me a sec. Yeah, we are looking only on the left. We are not looking on the right, because on the left data set and in AEC, what we say these points and these points should stay at the same positions. What we allow, it's only some curvature between them. And you see a very interesting thing here. We ask, you see, for Poisson ratio of -2. But then we say, okay, but we right now randomly have random preferences in the shapes. And right now, our system generated multiple solutions with Poisson ratio very close to -2, but with completely different geometries. And that's quite fun. So right now, we have the tool that allows us to have this variability in our design by keeping the property the same. So, and another thing what we did, we say, okay, now let's do it differently. Let's say we would like to have something that looks like this black curve, or if I put it into the unit cell, I would like our borders to look like that. And now I would like my Poisson rate to change my Poisson ratio. And I can go from -3 to almost 1, and you see how model tries to stay by the shape close to the specific guide curve. And that's again, it's exactly where you have this trade-off, and that's exactly why this model is really cool to use. Again, this is not direct variational autoencoder, it's not direct GANs, it's definitely not GANs, but I think Gary tried GANs, and GANs worked completely fine on this data set because this data set is relatively simple. So that's what we did. Again, this is not very much, it's generation, and I think even in the title we have, oh yeah, deep generative model. So this is one of the ways to generate. It's right now quite common. It's sort of, because when you invert some problems, you know, when you have the data set, let's say Poisson ratio and geometrical properties. So if you start with geometrical properties and try to predict Poisson ratio and try to train your model to do that, it's quite easy. It's called forward problem, because for each geometry, you have only one solution. Because if you have geometry, you have only one Poisson ratio, no other options. But if you just invert it, you have a problem. Because now, for the same Poisson ratio, you can have multiple geometries. And when you will train your model if you will try to train your model, you have a big trouble. Because again, your model, for instance, see something that looks, okay, if I just remove completely geometry from that, so your model look at the input, and input 1, let's say, okay, let's do a very simple example. Let's take the function as square. So let's take x square. So our y is x square. So forward problem is extremely easy to do. So your train data set in this case will look like that: 1, 1, minus 1, 1. Let's say 2, 4, and like minus 3, 9. Right? So this prediction is extremely easy to train. It's basically you have one-to-one correspondence. Unfortunately, you already probably see the problem. So now my model goes through the samples during the training. Oh, nice. And first and now I'm doing in reverse. So right now I would like to do a square root. So, and in this case, my data set is different. My data set is, I have 4, 2, I have, okay, 1, 1, and I have, if I just invert my previous data set, what I will also have is I will have something like that. Minus 3, 9. Just switch input and output from the previous. And now you see what's happening. My model, okay, say, let's pick 1 and 1. Okay, nice function. So I know that when I have 1, I need to predict 1. Like, okay, I have 4, 2. Nice. If I see 4, I can predict 2. My model starts to build some sort of maybe nonlinear extrapolation. And then immediately what happens, it takes 1, and now I tell in my training data that you need to provide minus 1. And model already knows that you need to provide 1. So it's absolutely, actually, it's not, in this case, it's called ill-posed problem. And we tried it because our reviewer for our paper asked us to do that. And you cannot train anything because, again, you have 2 outputs for 1 input. So what you need to do, you need to be quite creative, maybe add some additional parameter, let's say like noise or something like that. And in this case, you are not having this 1 to 1 and 1 to minus 1. But what you can have, it's 1 some noise, I don't know, parameter alpha will correspond to 1, and 1 with parameter beta will correspond to minus 1. So you add an additional trick, you add additional noise, or you do other tricks. So again, that's why just simple inverting of the problem doesn't really work. And another thing that I would like to show, it's another paper that's not published by us, but I find it's quite interesting and good. And it should be on my class 2, this one. Let me just copy it into the desktop. Again, this is also about exoticity. It's deep learning, doesn't have the anything related to the generative in the title, but it's generative model at the end. So this is graphical abstraction, and you probably already start to see something here, but I like this picture when they sell the method. This is our conventional method to design, let's say, auxetic metamaterials. So material with negative Poisson ratio. We just try to play with the geometry when they do finite element simulations or some mechanical testing, and then we get Poisson ratio. Again, forward problem. So what they are saying, it would be much cooler to say, I want Poisson ratio, and I want Young modulus. I would like to feed it in some neural network and get geometry, get the image of my structure, of my texture at the end. And that's exactly what they are doing here. So I will not go very much through the details, especially regarding mechanics. It's a little bit harsh things with the force rank tensors. But I would like to point your attention, first of all, to this, SIGIAN. And that's something that Gerrit already mentioned. SIGIAN translates as conditional GAN. So right now, remember, he added labels for 6 and 9 for the numbers in MNIST data set. So now what they're adding as the labels, they're adding properties as the labels. So in this case, they don't have a classification. They have regression inside of the GAN. And so I would like to show quite interesting picture from them. So they generate, of course, in order to train this GAN, you need to first of all generate geometries and get mechanical properties somehow, either experimentally or using finite elements. And that's exactly what they did. They used so-called Voronoi diagrams. I think you may be familiar with that. Have you seen this method of generation before? Okay, if not, you will probably see it in a computer graphic and everywhere. It's like it's a very common way to generate something that looks like that, because it's hard, by just putting some numbers, some points inside. Like here you have, I don't know, 1,000 or 100, sorry, points inside. And then according to specific rule, you sort of grow these grains, and then you smooth that and get this. It's Voronoi tessellation, one of the most powerful methods to generate any structures. So they generate 100,000 geometric patterns, and they test it in finite elements to get Young modulus and Poisson ratio. So what they did next, when they looked at the data, this is a very important thing. Remember, Gary talked about the probability distributions and a good match between what's happening in a trained data set and what's in real data set. So if you look at the randomly generated patterns, what they get almost all the forms, almost all of these geometries to have a positive Poisson ratio. So this blue one. And after training, just jumping a little bit ahead, what they get something here. So that's quite interesting. I was really confused by this diagram, to be honest. But this is a data set that they have. So you have the Poisson ratio and you have a Young modulus. So your Young modulus in their case shifted from let's say 2 to 14, and Poisson from minus 0.2. It's actually somewhere here to 0.4. So that's what they had at the beginning. And then if you look at that scheme here, you see a very, very familiar structure, except it's rotated. So you had noise, exactly what Gerrit showed, and you had these labels. Remember this C in the green square that he did. You put into the generator absolutely the same thing, and generator produces some loss function. So Gerrit combined them together, but in general you can calculate loss function. And then this results, there is a small difference. These results go to two different models. Discriminator, with the task to actually distinguish real, fake, or real. So if you feed it with real data. So the idea is the same as Gerrit described before. And what they call solver, when the task of the solver is do not care about label, about the fake or real data, but just try to predict Poisson ratio and Young modulus. This architecture is extremely similar with what Gerrit described. In Gerrit's architecture of SIGIAN, these things are combined. And to be honest, in classical case of SIGIAN, they are really combined. This, what is called? Regress. Yeah, there is some. Again, this is a little bit different name, but the meaning is absolutely the same. And after some training, honestly, they don't have a very good results, in my opinion. This is what they're showing. So input young modulus and output young modulus. It's results that for you may look very, very bad. And this is a comparison between Poisson ratio that they wanted and the Poisson ratio that was produced. And actually, if you look at that, you see this exactly diagrams here. So what they want is something above 0.25. And what would they get? It's something actually beyond 0. So this yellow, this orange distribution. At the same time, I would say if you train GANs, this is not so bad. This is not so bad, and one of the proof that it's not so bad that the fact that their paper was accepted and published. So this is what they had, and I think they also have they also did some experiments, quite nice. They produced these forms using 3D printer. Again, a little bit of more, and they actually use COMSOL as well, to be honest. So you see a little bit about the architecture itself. This is mean square error for the Young modulus and Poisson. Again, classical mean square error, nothing fancy. And again, I will not discuss the stability things. And what I would like to show you is this example. So what they want, what they wanted to have, what is predicted by neural network, like they wanted to have Poisson ratio minus 0.3 and Young modulus of 3, and what they get, oh no, this is what they generated, sorry. And what they actually had, if you run on the same structures, finite elements models, you will get minus 0.2, depending like from minus 0.2 or minus 0.27 and so on. And Young models will also change a bit. This is not so big difference. In this case, probably they pick the best, one of the best samples. And here you have the error on average 15%, and it's quite good. Because if you look at the structures on the top, they are very different. So maybe they have the same from the same family, but exact shapes are very, very different. So they also successfully solved this problem of generation of multiple different options for the same properties. So yeah, and then again, this comparison with experiments probably not so interesting. I will also probably upload this paper because I think it's really easy to understand what's happening here. And they also, similar to Garrett, they mentioned, let me find it, three network structures, and they also, I think, called it three agent, 3-player games. Yes. So again, usually you refer honestly to GANs as a 2-player games. Again, example with a money counterfeiting. But in this case, since they involved this what they call regressor or predictor, I don't remember, they call it the third player, but this player is not competing actually. It's just getting the data and predict. So you can, in some cases, why it's possible and why it's maybe sometimes reasonable to use this separately, because you can train solver without touching discriminator, and vice versa. But again, this is very application specific, so we will not go into the details for that. So I think on this point, we gave you quite a good examples and quite good introductions to the generative neural networks. We will continue that in the next class because I think we will be able to show you much more advanced and state-of-the-art things that, again, you know this DALI, you know this stable diffusion. They're all based on the specific neural network approach called diffusion models. So, and they're quite fantastic. I still have not full understanding why mathematically they work, but the results are absolutely fantastic. So we'll talk about that, and we will give more examples from the literature, and we probably will just go through a couple of papers more. So yes, on the generative models, lecture number 1, I think we have done here. So if you have any questions, just please. What we've done with Garrett, right? Yeah, give me a sec. You're absolutely right. Why it's not? It's open here. Ah, yes. So you mean this symmetry between this, yeah? Yeah, I understand which picture you are referring. So it's symmetrical. Yes, symmetry was a part of the plan because this is initially in our data set was a symmetry. So we didn't care about this particular, let's say, curves here because we just define one of them and then use it for and then mirror it. That's actually our output. So you see, this is if you put it on the rotate and put. One of the reasons why we did that because first of all, from mechanical point of view, if you don't have the same curves on the sides, you have additional components of the stiffness tensor. But in this case, it was even more straightforward to see what's happening. Where is the mouse? Your unit cells that you probably will be able to see in the picture number 1. Give me a sec, Gerrit. I will find it. I think we have a nice illustration of that. Yes, here. You see the problem? If you will change, let's say, this one to another one, it will not stick to the neighbors. So therefore, they can be considered as unit cells. Right now, actually, we are working with another colleagues about the system that will allow us to change curvature everywhere independently and get much more exciting results. But if you want periodicity in this particular design, you are forced, really forced, to consider only one curve.
So how this is actually done? Parameterize this curve, just one curve. And this curve is given by basically a straight line. It's imaginary. Then you select 5 points. Based on these 5 points,
yeah, this is exactly what's happening here.
You somehow get it. The nice thing is that each of these points, you can represent the position of the point just by a number between 0 and 1. And you select one number of 5 points, get 5 numbers between 0 and 1, and everything between here is actually an admissible design. So if you remember the autoencoder, when I said that you do this in coding, but you don't know how this distribution looks like. So you might have some samples actually from 0 to 0.1, and then you might have somewhere from 0.9 to 1. And if you select something here, you don't know where it is. But this thing is so nicely chosen that you know whatever you choose between 0 and 1, that's a nice design. So you don't need to worry about the sampling outside of this admissible design. That's what makes this problem so special. It's a nicely solved.
Yes, even with GANs. Even with GANs, it works as we have another problem, and Gerrit's struggling for that problem for already almost 2 years, but we are close to the end. When you don't have this properties, in particular, I can draw it directly on the screen. I think it will be easy to see in this case what's happening. So let me just add a new. Oh no, I wanted a new slide. So that's how the problem itself looks like, and we will probably discuss some limitations of these things. So the problem looks the following: we have a sheet of paper, and now we have some periodic grid inside. Let's say 3 by 3. That was wrong position, but doesn't matter. And what we would like to do, we would like to cut straight lines there. We just want to have a cuts. Why? Because if you do that, you can have a quite cool mechanical properties. Let me just, in this case, show you this mechanical properties on this. There is a quite famous paper. Grima cuts. Yes. So and so if you have the let's say rubber sheet, okay, accept all, and if you just rubber and you do pulling, it will actually shrink because rubber has a positive Poisson ratio. But if you cut something inside, you see you will get expansion. So, and this is a so-called classical problem of rotating squares. I think maybe there is some example. Okay, there is no in. It's in my paper. I think it also was there. Wow, you can see it here. So if you have a system with rotating square, like with the squares, I can bring a sample next time. You have a Poisson ratio of -1. So, and the idea that, let me go back to the presentation. Basically, in this case, the idea is the following. So what you can do with the cards, you can take and do it in this alternating pattern. And in this case, you will have something very close to -1 in Poisson ratio. Yes? Oh, why it's doing that? So something like that. At the same time, what is interesting for us, what if we rotate these cuts? So what if we will take and consider the case like I can do this eraser here. Okay, I can do that like that. So what if I can randomly, funny, rotate the cuts. Again, the red point is not in a proper position, so that's why I shifted. So what would be with my Poisson ratio? Do we see a problem with the design space that we have right now? So in this case, what we will store the rotation angle here. And in this case, we have 9 rotation angles, A11, I alpha 33, yes, this matrix. So, and we would like, based on these inputs, predict Poisson ratio and do it inverse. We would like Poisson ratio, how we need to cut it. Do we see a problem that doesn't exist for the curves that we considered before? Right now, actually, there is no problem. Honestly, if we just use exactly the same length of the cuts, we have no problems. Because any values of alpha between 0 and 360 will be admissible. Whatever we pick, we will get correct design. However, since we like to challenge ourselves with strange tasks, what will happen if I will consider long cuts? Well, say with the same length. Now, I'm quite, again, I don't consider, so they will actually be here because it's periodic, and this one will actually go somewhere here. So now, you see the problem, since we cannot have some configurations, because if we, for some reason, decide to rotate this cut, okay, I will draw one cut and another cut. And there is some center, and there is some center. If I would like to rotate this cut here, what I will have intersections between them. And if you have these intersections, it will ruin your properties quite well. Again, your material can actually disintegrate because you cut some hole inside. So, and due to that, so let me just show the case which is bad. So it's from the center. This is definitely a bad case. So now, if we look at all possible values of alpha 11 and alpha 3, or through alpha 11 to alpha 33, we actually have some restrictions inside. And now, if we directly try to train GYAN, it may generate us a lattice, or not lattice, a material or cut pattern that will have intersections. And that will create a bad design. And it will do that, unfortunately. If you just train GYANs in straightforward manner, you will get the solution. You say, I want Poisson ratio minus 0.5. It will say, okay, take something like that and you will be happy. But I know from experiments and from simulations that will not give me a 1.5 because they will consider intersections. So that's a problem when we tried multiple solutions with variational encoders, with just encoding the latent space in a different, try to create a good mapping, try to create the space when we can, any peak in the space will give us legitimate design. Unfortunately, it's really hard. So this is another limitation of GYANs associated with if your design space is not nicely connected and continuous, You have a big problem because your models, your GANs will generate lattices or generate systems or generate buildings that will not make sense. And this is something that you need to always take into account when you do inversion of any models, not even in machine learning, actually in optimization problems as well. So if you do, are you familiar with the topological optimization a bit? So you know the problem, you may have separated pieces that are not connected, and you need somehow to take that into account, and sometimes you have penalties or whatever. Very similar thing, much harder to control because it's more or less black box training. So in optimization process, at least you see what's happening. Here, why it's creating intersections, why it's going there. There is some, of course, we understand it, but it's really hard to explain mathematically. So on that note, I think we done. Second time already for today. Any questions? If not, please, I will really ask you to start. Gerrit, something happened with the home project too. You created something. Yeah, so please do home project 1, because with the generation after the second lecture and on the next, not this week or next week, we will give you a third project when you need to generate something. And again, since you haven't submitted anything for the home project 2, I really encourage you to do that, at least for us to see what's going on. So, but at the same time, Gerrit, what's your comment?
Last time we tested other folders.
Yeah.
You might notice that you're
yeah.
And that's actually a way to change that. So we can create some sort of exercise, but we need to put there.
Okay.
And I recommend this method.
Yes, we'll do that. So yeah, we will delete this folder because it's empty right now, and just upload it using here, because in this case you cannot see work of each other. Because for the home project 1, we didn't care about that so much, since it's guidance home project. Here it's really creative. So, and to be honest, if you will just copy, it will be quite visible, because right now you have much more room to improvisation. You much more room to just create, pre-process your images, what to do afterwards. So, but please upload it to this second home project. If it's bad, if something is wrong with that, just let us know, okay? So yes, in this case, thanks a lot for Gerrit for this lecture. I think it's very, very good, and thanks a lot for you for being here. Thursday, nice exercises regarding generation. Next Monday, generation part 2, plus maybe a little bit more. And we are getting close and close to the end of the semester. And I think right now the evaluation thing, have you received something regarding evaluation of the courses? I think you have a deadline until 9th. So please do that, because it's important for us as well. Because if we get less than 15% of the participants evaluated, they start to ask, 25, they start to ask why. So please do that. I will remind about that during the practice session again. And if I will not see a lot of these results, I think I can trace how many people voted. I will do that during the class. So yes, thanks a lot, and yeah, have a nice evening. We'll see you on Thursday. Let me just switch it off. Oh, I saw that it's okay. It's not muted. It's nice.